Hello, ladies and gentlemen. We're going to do a lab regarding torque, and we're going to use a meter stick on what they call a knife's edge, and a holder here. You can see that the meter stick is balanced because it is balanced at the middle. We have a little bracket that we can unscrew a little bit and adjust and hold this pivot point at different positions along the ruler, but obviously if I don't have it positioned at its center, it won't stay balanced. So you would think that the center is 50 centimeters on a ruler, assuming the ruler is made well and pretty uniform with the mass on each side. Same density everywhere. Sometimes you get a ruler which, for whatever reason, it's a little off. The density on the one side is maybe a little more or less than the density on the other side. But this ruler is pretty good. I put it at 0.5 and it stays pretty balanced. I'm pretty impressed with this one. I do have each side of the ruler on opposite sides of the pivot point labeled, point A, or side A and side B. That way we can tell what side we're hanging things from, because that's what we're going to do. We're going to hang things from either side of the pivot point of this ruler. And you folks have a lab, although the instructions are not clear because it's just really a data sheet. The lab is going to ask us to put masses on either side of the meter stick and see if we can get masses to balance. We're going to tell you what to put in place on side A of the meter stick, and then you are going to have to figure out where mass B will make this equal. Now, of course, that's because when you put masses on either side of the pivot point, if they hang accordingly and they balance each other, those torques are canceling each other out. And that's important to realize. The torque on the one side is going to be balancing the torque on the other side. That way, you don't have any rotation, or you have fighting rotation, right? You have fighting rotation on one side, being pulled by the rotation, trying to rotate it on the other side. So in order to, give you a feel for this, and unfortunately, you're not in the room doing this, but we're going to take these little brackets, and we're going to hang it at 10 centimeters away from the pivot point. Your data table says to hang it at 10 centimeters. What's not clear in the data table is really what that means is to hang it 10 centimeters away from the pivot point, not 10 centimeter mark. And so there we go. I got this little thumb screw. I can put that bracket on there. Now you can see just the mass of that bracket itself, that little bit of weight has caused an uneven torque around that pivot point. It's creating torque on this side, so it's rotated this way. And if I put this bracket on the other side, assuming the brackets are relatively uniformly made, and I put it at the opposite 10 centimeter mark, again, I can get that to balance. But unfortunately, I don't want it just I don't want just the bracket. I want 200 grams. So I'm going to hang 200 grams here. And in the lab, you're going to take this 10 centimeters and the 200 grams. And that weight, and we're going to say they're hanging straight down compared to the meter stick. So we're going to say the meter stick is horizontal. We're going to say the weights are vertical. And that gives you a nice 90-degree angle when you calculate torques. But you have to calculate torque, you got to convert everything to meters and to kilograms. So you have 10 centimeters that has to convert to meters. You have 200 grams. We're going to have to calculate to kilograms. Yes, there is mass of the bracket, but since the mass of the bracket on the one side is equal to the mass of the bracket on the other side, we're going to say that those masses almost cancel each other out. That's a little flawed, but it's good enough. So the first row on the data table says to hang another 200 grams and find out where is this going to balance the ruler. It doesn't give you the location. You have to find the location. Well, common sense says it's going to be the same mass, it's going to be the same distance, right? If you're 10 centimeters away from the one side, you figure you'd be 10 centimeters away from the other side, and you know, we're getting there, pretty close. Try to get this as horizontal as we can. I didn't even lock down that thumb screw. I just have it balanced. And yeah, I mean, it's pretty good. You know, 10 centimeters. Let's say 10.0 sig fig wise, I guess. And pretty much 10.0 over here. It's pretty dead even on either side, which would expect, right? The torque on the one side is being canceled by the torque on the other side. The pivot is trying to, I mean, this mass is trying to make it turn counterclockwise, and this mass is trying to turn it clockwise, and they're battling each other and canceling each other out. Which is what we want, nice and balanced. Well, in the second row of the data table, they don't want 200 grams. I'm gonna hang 100 grams. And obviously, that's not enough, right? The 200 grams winning that battle in terms of the torque. So we're gonna have to find where is this 100 grams going to be able to balance the 200 grams. And we're getting kind of close. Close. And that's pretty good. Yeah, I'd say that's pretty good. I have to get my glasses to read these little lines. So, I would say this is 68 and a half, but that's from the 50, so that's 18 and a half. So 18.5 centimeters is where this 100 gram mass is being balanced out. And so we're going to enter that in the data table and do the calculations. You should say that torque A is a positive or a negative sign. One's got to be positive, one's got to be negative. If torque A is always counterclockwise, I guess torque A's can be positive, and I guess our torque B's will be negative, and that's fine. That works. All right. Well, then the next part of the lab asks us to hang 50 grams and see where this equals out. So obviously, notice there's a trend. The less mass I have, the further out I gotta go, don't I? Yeah. Oh, that's gonna be nice if it turns out right there. And it's wiggling around a little bit. What happened? So that's 82 and a half, but that's from 50. So that's going to be 10, 20, 32 and a half, 32.5. 32.5 centimeters for the 50 gram mass hanging there. Okay? So now we have the first three data rows of data. In the next three rows of data, we get to change it up. We are no longer going to hang the meter stick at the middle. We're going to change the pivot point to a different part of the meter stick. So I'm going to, kind of pause the video and regroup, and then come in and show you the second half of this exercise. Okay. So like the lab states, we wanted to move the pivot point to the 30 centimeter mark on the meter stick, and we move the mass to 10 centimeters away. So that's at the 20 centimeter mark of the ruler, but it's 10 centimeters from the pivot point. And now we're going to balance that torque with another mass on the other side, just like we did before. Notice, obviously, with this pivot point, it's not at its center. But with the addition of, masses on either side, we can still get this to balance. Now, it may look a little freaky to some, but that's okay. So what we're going to do is we're going to take this side,
And we're going to take the 50 gram mass, and we are going to find where can we get this system to balance without these shaking around too much. And we're getting close. Get closer. There we go. So we're pretty close to the pivot point. We are 4.5 centimeters, 4.5 centimeters away. And that's the 50 gram mass. So that's your fourth row of data. It's balanced. Pretty good. Now we'll do the next one, where we're going to move on from 50 grams to, I believe, 20 grams. And we're going to find this balancing point. And not too far away. That's pretty close. Yeah, I'm not happy. There we go. I'm pretty happy with that. And that's 8 centimeters away. 8.0. You know, we're pretty much right on the 8 centimeter mark there, from 30 to 38. So 8.0 centimeters away for the 20 gram. And then got this little itty bitty 10 grams. And we're going to put this 10 grams. Close. Pretty good. 11.0 from 30 to 41 centimeters. So now we have all of the data on the data sheet. And now you need to calculate the torques on each side. Again, one side's positive, one side's negative. There are 2 blank rows down there. Don't do anything with them. You can leave them. But as the directions state, I want you to show some calculations for at least one of the last 3 data sets. I don't really care about the calculations. I mean, I do care, but you don't have to show the data calculations for the top 3. But for one of the bottom 3 sets, I need the torque calculations shown and written out. And then there's an interesting question, the second question, which I expect a well thought out and proven answer, not just a quick answer. Okay? All right, get to work. Thanks.